Welcome to Lab 4, the physics of extreme sports with ropes. The order of this presentation will be introduction, which includes purpose, parts of the experiment and results, the code or theoretical explanation, which includes tracker video analysis, the initializing data and the code, the follow-up questions, and finally the conclusion. The purpose of the experiment was to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. The parts of the experiment: we had to use tracker to extract the information from the video that we were given, create a computational model to simulate the motion of the spring mass motion of the video. The results that we got were that the computational model predicted the motion of the experimental data accurately, only it took longer to arrive at the same position. Now let's take a look at the explanation. First, the tracker video analysis. This is the video that we were given by a professor, and as I play it, you can see how the position in the Y direction changes in an oscillating manner, and the same for the change in position in the X direction. In this video, we know that the origin is at the top of the spring where it's attached, and that this length is of 0.7 meters. The data that we get from the change in position, we extract and we use for our code in VPython. Now we'll look at the data that we use to initialize our program. So the origin is the place where the spring is attached. The mass is 0.402 kilograms for the ball. Our initial position taken from tracker is in the X direction negative 0.114 and in the Y direction negative 0.634 meters. Our initial velocity, because it's at rest, is 0 meters per second. Our delta T was told to be 1 over 210. Our gravity constant is 9.8 meters per second squared. Our spring constant, which we calculated, is 6.099, and our L naught is 0.123. Now let's take a look at the code. This is the code that I used to set up our experiment. This first part is for the visualization of the graph and the screen that we'll see shortly. The mass of the ball, position, velocity are all already set up. Our time is equal to 0. This part is to extract the data from our CSV file from the information we got from tracker. Our delta T, gravity constant, spring constant, and L naught are all set up. And then we calculate S through L to be able to calculate the net force of the spring on the object. We know that our energies are kinetic energy is 1/2 times the mass times velocity squared. We have two types of potential energy, which are the gravitational potential energy, which are mass times gravity times the position in Y, and our spring potential energy, which is 1/2 the spring constant times S squared. Then we have the part where we update the position of the ball and the spring by using the forces. We calculate gravitational force, spring force, and then our net force, which is just the sum of the two. We then update the position of it through this part, and then we update the energy. So we have kinetic energy again, the change in kinetic energy, the gravitational potential energy and its change, and the spring potential energy and its change. This is what was produced by the code. Now for our follow-up questions. It says, for your model system, is the energy principle satisfied? And second of all, using the data you obtain in tracker, make two separate estimates of oscillation periods. First through the X position and second through the Y position. So for the energy principle, our yellow line, which goes straight through 0, is the change in the system's energy as a whole. Because it is 0, we know that the energy principle is being followed because the sum of all the energies that we have in our system or are related to our system all add up to 0, which means that energy is being conserved. So for the periods of oscillation, in the X position, the time for 3 periods is 4.84. Therefore, the period is 1.61. And in the Y position, we get that the period is 1.48 seconds. The conclusion is, no matter which process is used to calculate the period, it is always going to turn out to be the same. The difference or error found in these calculations is due to experimental error, and the difference is very insignificant. So, in conclusion, although the spring mass system computational model does a good job of predicting the motion of the block attached to the spring, the timing of it is slower than that of the actual motion, which could be due to a difference in magnitude of one of the forces that we calculated. Second, The energy principle is satisfied in this case because by adding the different energies related to our system, we find that the net change in energy is zero, which means that the energy was conserved. This is the end of Lab 4. Thanks for watching.